Okay, so I am recording. This is number 6 on 2-2. Enter a T or an F for each answer space below to indicate. Let me go ahead and click on this question here. Uh, True or false, you must get all the answers correct to receive. So
So number two is pretty straightforward. That was division by zero.
yeah, yeah, that's true. So that's clearly T. Number one, if the limit is x goes to 1 of f of x times g of x exists, then the limit is f of 1 g of 1. Is that necessarily true? What do you guys think? So I'm going to temporarily, want to see how I best want to do this. Because I want to be able to toggle back and forth between the question. I can verbalize through this. Um, the limit does not have to be the functional value. The limit can be, you can have a situation where the graph comes to an open dot or an open point, and then the point itself might be just somewhere else. So number one is not necessarily true. So it would be false. Okay, so it's not always true, therefore it's false. I'm going to copy the question down. You know what I'll do is I'll go to my overhead, my camera, and draw a picture. I'm just copying it down. All right, I'm going to stop the share. I'm going to go to my overhead, and I'll come back to this if I need to. So, um, pin this so it's bigger here. I apologize for the not the most, not the greatest camera ever. Hopefully, you can see that. Basically, this is just a question of if a limit exists, you could have a case like this where you have an open dot. The functional value might be up here. Okay, this could be your f of 1 g of 1. This could be just the generic function f of x g of x. So the lim exists, but it's not necessarily the functional value. That's all it's saying. So that's for number one. That's an example of just the case where it might be an open dot. Okay. Um, Let me go back to the problem. If f prime of 1 exists, then the limit as x approaches 1 of f of x is f of 1. What do you guys think? Well, yeah, I'll just jot it down. Let me just put the other two down here. This is C. This is actually part 3. Part 4 is if f of x is continuous at A, then it's differentiable at A. And 5 is the other way. If f of x is differentiable at A, then it's continuous at A. Okay, so I'm going to go to my camera here. There you go. Actually, the 3 and 5 are kind of the same question. So if the derivative exists, there must be a point at on the function for the derivative to actually be there. And so, yes, this is true. The point has to be there. We can't have any discontinuities. So the limit must exist and it must equal the functional value. This is really just the definition of continuity. in one line. So differentiability implies continuity. So that is the same for part 5. Now, number 4 is the converse of part 5. It's basically just flipping the two statements back and forth. If a function is continuous at a point A, does that necessarily mean it's differentiable? And in the case like this, the answer would be no, or false, I guess. And that's because you could have a case like a corner. You could have a absolute value graph that has that V shape. It's continuous at 0, but it's not differentiable at 0. There's no way to put on a unique tangent line at that point. So differentiability implies continuity. But not the other way around.
That makes sense. And the same thing applies to holes.
Yes, exactly. Holes are just an example of discontinuity. So if we go back to that first example, that's just a case of one way that the functions could be not continuous. All right.
I have a follow-up question with that then. Can you can differentiate at any point on that line but that hole? Does that also mean that, I mean, you can still differentiate the equation,
Yes.
differentiate the function, but not
Yes.
necessarily that particular hole.
Yes, exactly. You can still
Okay.
differentiate elsewhere. When we talk about discontinuity, we almost, well, it's good form to always tell where it's discontinuous. It's not sufficient to say this function is discontinuous. You need to say this function is discontinuous at x equals 2, for example, because then elsewhere we're assuming it's continuous and therefore potentially differentiable. Now, it still might have corners. That's another thing we have to deal with, but it could potentially be differentiable. Okay, were there other follow-ups to this one? Okay, so somebody asked about 2.1, numbers 2, 5, and 6. So let me go to that. So 2.1. Let's look at number 2. Copy that. So 2.1, number 2, we have a ball is thrown straight up into the air with initial velocity of 100 feet per second. Its height in feet after t seconds is given by y equals 100t minus 16t squared. Find the average velocity of the time period beginning when t is 1 and lasting for 0.1 seconds. And of course, you have a couple other here. So, and then we'll infer the instantaneous velocity. Okay. So I'll stop this share. I'll go to my overhead here. So we want the average velocity from t equals 1. And so in the first case, we're just going to do a slope between f, we'll call this function f of t for, it'll make notation easier. F of 1.1 minus f of 1 all over 1.1 minus 1. Now, in the first case, f of 1, we can just plug that in. That gives us 84. On the bottom, we have 1.1 take away 1, which is just 0.1. F of 1.1, you know what? I got to go get my calculator. I'll be right back. So just plug in the 1.1 into the function. So 100 times 1.1 Take away 16 times 1.1 squared. We get 90.64. We do a subtraction, so 90.64 take away 84. 6.64 over 0.1. And that works out to be 66.4. And that would be feet per second. And then you just do it the same with the other two. I'll tell you what, I'll skip up to the bottom one here. Let's see what happens, because the trend will be pretty strong. So f of 1 we already know is 84. On the bottom we have 0.001 after the subtraction. I just need to figure out what the function is when I plug in 1.001. And I get 84.067984. So when I subtract, and I don't want to drop any decimals here, I get 0.067984 divided by 0.001. I get 67.984. Sorry about that. I'm running out of paper there. And it looks like there's a trend. It looks like it's trending toward 68. So I would hazard to say that at exactly 1 second, the instantaneous velocity is going to be equal to 68 feet per second. And that's basically based on this trend here. Now, if you're in doubt, you could always take another value closer. So you type 0.0001, for example. Now, this is section 2.1, and you're at that boundary between just before you're being taught derivatives. If you've already gotten to the section with derivatives, you're probably going to discover that you can do this problem in a matter of like 2 seconds. So you would take the derivative of the function and then just pop in the number 1, and you would get 68. So I can tell you that this answer is correct. Now the trend here is pretty strong. But you know, if you've already gotten to the lesson on derivatives, then you would just take the derivative and you would see that the answer is 68. So this was 2.1 number 2. Anybody have any comments on this one, or any needed explanation?
I just think I gotta learn how to do derivatives because I did it by definition.
Well, this is the way you were meant to do it on this question. I'm just saying that you will probably see very soon the derivative lesson, because it's coming up. If it should be coming up in chapter 2 anyway. And you would see that this problem reduces down to a fairly quick calculation. So you're at that point where you're learning, you're kind of doing the derivative, but you're doing it the algebraic way.
Yeah.
And one of the things you're kind of hopefully picking up here is that these values right here are your delta t. These are your little changes in time, and you're letting these go to 0. So a derivative is a limit of the difference quotient. So when you're taking these slope formulas and you're progressively letting the interval shrink closer to 0, you are in essence doing a derivative. So this is a derivative done algebraically. And the good news is, once you learn your derivative forms, these problems are a lot faster. You kind of have to earn your way to do that. Let me go back. So I know there's a few other questions. There's a question, so we won't be penalized if we use derivatives to solve. You know, frankly, on the test, you just do what you got to do to get the problem figured out. What about using L'Hopital's? I don't know if you really need to use it on this one. I'll actually have a comment on that one, because that's popped up a couple times in the ed discussions. L'Hopital's is nice, but it's not always the shortest way to do a limit. And when you get to the L'Hopital section, you're going to be given some questions that are frankly rather rough. And one of the things I always tell my students is I say, I don't really care how you find the limit, just find it. And if you're in doubt and you don't like the algebra and everything's getting messy, get your calculator out, put in the numbers, and just get progressively smaller intervals. You can actually do a very, very effective limit on your calculator just by basically doing what we did right here, just working them out numerically. It's not pretty, but it works. All right, so let's see. I'll go with what we had here. So the numbers 5 and number 6. So I'm going to go to go back to the problem here. Let's see, what was number 5? Oh, this guy. Yeah, these two, in fact, I'm going to keep them both up on the screen here. These two are both kind of related questions. And they're kind of interesting questions. They have some bizarre behaviors here. Let me copy them down real quick. Let's see. At 8, yeah. These are actually continuous graphs, believe it or not. Both of them are kind of similar looking. All right, so I'm gonna go to my overhead. The question is asking, actually, what is the question? Give me a second. It's asking whether the derivative exists at 0. Okay. What you have here is a sine function of a quotient, and what happens with these guys is, let me come down here. If you graph 1 over sine of 1 over x, you get a really bizarre graph. It looks something like this. It's kind of a nice sine wave, and then it starts to get crazy like that. And then similarly on the right side, it gets crazy before spreading out. Okay, it's a bizarre function. The problem is that at 0, well, what the heck is going on here? So this is where you kind of look at the exterior. So these functions on the outside, the x and the negative 10 of 10x to the 8, act as sort of envelopes. And in the first case, x by itself, if you were to graph the function x, and because the sine function goes up and down below the up and down above the x-axis or like that, you actually create what looks like an envelope. And so the graph is going to look something like this. It's going to get real scrunchy as it goes toward the origin. That's what the graph is going to look like for the first one. For the second one, it's going to be similar, except that this envelope functions looks like this. It actually has a much more rounded shape like that. And so that the sine graph will get all scrunchy, but like that. Okay. Really, what's happening then is that we're looking at the behavior of x. As you approach the origin on the first one, the slopes of the x function are always either 1 or -1. So it doesn't ever zero in on a particular slope. So in this case, f prime at 0 would not exist because it basically bounces between -1 and 1. Okay. Whereas here, you'll notice that if you were, if you notice the graph, it actually flattens out. So here you can see that, ignoring the sine wave for a moment, just looking at the dashed line, you can see that the graphs are flattening out. So as x approaches 0, this derivative here approaches 0. Another way to do it, well, let me finish that off. Here, f prime at 0 does exist, and it equals 0. And then one way to kind of see that is to create what's called an envelope. So you take the x sine -10 over x, and you know it's going to be less than x or bigger than -x. Okay, over here you do the same thing. And the 10 is just decoration, doesn't really do anything. We got your regrets. Actually, I realize now I probably should have them the other way. I'm just going to chop off the 10s. All right. And so you're basically trapping this function in between its envelope functions. And since both of these ones here trend to 0, the derivative this is all at x equals 0. The slope also equals 0. I apologize for my sloppiness. Here, unfortunately, the derivative here trends toward 1. This one -1. This one trends toward 1. And we don't really get like a nice, I'll put a big question mark. It doesn't really go toward a particular value. All right. This is a pretty interesting graph here. This is crazy stuff.
That one is a really tough one to wrap your brain around, and I'm not quite sure why. Does the power rule like nah, I won't ask it.
Well, I guess the best explanation I can give is just looking at the picture here. In fact, if I was to do this in class with you, because I probably wouldn't even bother with this stuff. I mean, it's valid, but I don't know if I would bother with it. I would try to explain it with the graph. You've got the X graph, this guy right here, but also its mirror will be here. So the sine wave is going to be trapped between it. And this X graph, well, when you're at the origin, what's the slope? It's either 1 or -1. So the sine wave gets trapped in there, but it doesn't get trapped toward a particular slope. Whereas here on the 10x to the 8, whether it's negative or positive doesn't matter. You still get the same envelopes.
So you're referring to like an intersection of two functions versus just the two functions touching.
Yeah, these are actually this function here is trapped between its envelope functions, its outer functions. So the behavior, if I cover up, let's say, and I just have 10x to the 8, and then also its negative version, basically I'm going to get these two dashed graphs here. This whole graph is actually trapped between them. So the behavior of this graph will be found by studying the behavior of just its envelope graph at 0.
I think that makes sense.
Okay.
Sorry.
This is
Sorry,
one of
go
those.
ahead.
There's really not. You don't really do a whole lot of math per se. You're not doing much calculations. It's much more of a concept of, can you see the derivative in action purely based on the pictures? And I'll admit this is a challenging question. Part of the reason we asked it.
Would it help to say, and I'm not sure if this is correct, and correct me if I'm wrong, that you can conceptually see a tangent on the bottom graph where the top graph you can't?
Yes, exactly. So if I were to draw the bottom graph without just its envelope, not the actual function, you can see that the way they touch each other at 0, it's tangential, like that. Whereas on the top graph, the x and the negative x graph don't actually touch each other tangentially. In fact, they pass right through each other. So it's either doing this or this. Which one is it? Is it, well, we can't make that inference. All right, I'm looking at the chat here. Will this Q&A be published for later viewing? Yes, it will. Can we ask about the upcoming exam too? Like, what are we allowed, not allowed on the exam? Yeah, in fact, I'll be sending a lot of emails out about that. I haven't done that yet. The exam is on the 7th, I believe, and I usually get things set up a couple days beforehand and then send out emails. So I'll probably, like, on Monday or Tuesday, I'll start sending you all these emails. I don't want to overwhelm you right now with that because it'll get lost in your email lister. But you're one of the differences here is you're going to be not allowed to use your normal calculator, but you will be allowed to use Desmos. So one of the things I want you to get used to doing is try doing some of these questions on Desmos so that you know what the button sequences are. And other than that, it's pretty much a traditional exam. It's questions chosen from the homework list. And now one of the things I'll also mention in the email to everybody is once these lessons close, you should be able to go back in and redo them for just practice. Right now, when they're still live, my understanding is that you only get one other practice question and that's it. So it's kind of limited. So when they close, then I would recommend to go back in because you already got your score. Your score is set. You can go back in and just redo the questions for practice. And I've had a few emails come my way. I really, I don't really care how you find it. Some people, Khan Academy is also good. If wherever you can find information to help yourselves, go with it. We have videos on you've seen the videos embedded with it here within Infinity. We've got lots of stuff. If you go into the Canvas page, there's all sorts of lengthier videos. Hopefully you're watching those too. But if none of those are happening for you, look around. Khan Academy and Paul's online notes are two traditionally good sources. And so I'm not picky. I just want you guys to learn. Do whatever you got to do to learn. Do it honestly. All right. I'm gonna. What do I want to do here? Well, I'll just throw it open. Anybody have any other questions they want looked at? You can go ahead and just tap in audio or send it in the chat.
Can we go back to that 2.2 number 6? There was like 6 on there, and there was one more that I was having a hard time understanding.
Okay, yeah, let's look at these. I had this up originally, and then we then looked at another one. So this is 2.2, number 6. Let me make sure I'm in 2.2. Yeah. So this is the one you're asking about, right?
Yeah, I mean, if it'll be useful to the others in here, there's also another one that's up there a little bit that has 3 lines, and those 3 lines, you have to figure out which one is differentiated first.
Oh yeah, I know which one you're talking about. We'll take a look at that one too. I don't remember the number, but I think I can find it pretty quick.
So whichever one's useful for everybody else. I've been talking quite a bit, so.
Well, let's do this one. Let's just kind of verbally run through this one. If f prime of 2 exists, then the lim as x approaches 2 is f of 2. Now this is related to the one we did about 10 minutes ago. This is the case of differentiability implies continuity. Well, you know what? That's bizarre. It's a different question when I click on it. Sorry about that. Well, let's leave this one up. So for this number 1 here, its differentiability implies continuity. That is true. Okay. For number 2, if the lim as x approaches 2 of f of x g of x exists, then the lim is the functional value. That's not necessarily true. You could have a hole there.
Right, that's the one that we did before, right?
Yeah, I noticed that 4 and 5 look a little different, so I'm gonna hit those. 3,
Yeah, those ones.
yeah, let's just verbalize 3. If f of x is differentiable at a, then it's continuous at a. That is true. 4, oh, so we're taking the lim of this crazy function, and it asks, can we do the lim of the top and bottom separately? And the answer is yes, you can. So the number 4 is true, assuming it exists. But yes, you can do that. And number 5, same thing. I'm not trying to trick us. It's all yeah, you're just basically doing top and bottom separately. So the lim of a quotient is the quotient of the limbs. So 4 and 5 are both true in general. Now this assumes that the limit does exist. If the limit doesn't exist, well, it doesn't, it's the idea is still valid. So yes, these would both be true. All right, let's look at the one you were asking. I think it's.
Quick question about that last one.
I'm sorry, go ahead.
The question we just got done. Sorry, I was trying to figure out where the mic was, the mic button was. So you said the last four or five are true. Is that just asking for, does the equation on the right represent the equation on the left? Because, you know, if you input the limit for x, you'd have 0 at the bottom. So would that, so is it specifically asking, is the equation on the right the same thing as the equation on the left?
Yes, that's how I interpret it. It is a valid step to go from the left to the right.
Okay,
I think I had the same issue. I interpreted it that way too, and I entered true and it was incorrect. And then when I inserted the limit and got the output is on the equation from the left is different from the right. So on one of them, on the ones that I receive, my number is a little different than the numbers you have on screen, but when I inserted the function on the left did not equal the function on the right, so it was false, and that was correct.
Okay. Well, I can tell you that the
Was
step
my
here is valid.
experience too.
You can go from the left side to the right side. You can, the limb of a quotient is the quotient of the limbs, with the caveat being that the limits must exist. So this is kind of, you know, as I'm studying this, I'm thinking, you know, this probably could have been phrased a little better. This is a valid step. It's valid to go from the left side to the right side. But the limits have to exist. Now, if the limit doesn't exist at all, so if you plug in 3, what do you get? Looks like it fails. I guess the whole thing is a fail, but it's still a valid step. It's kind of a weird thing, but the limit does not exist for number 5. It's looking like 18 plus no, actually number 5, it looks like it might be 0 over 0. Well, I'll tell you what. My opinion is that this is a valid step. My opinion is that this question is being asked, is this a valid step to go from the left to the right? And it is. So I would mark true for both of these. And I'll tell you what, I'm gonna make a note of this one. I'll bring this up with the Affinity programmers and ask them, which is what the heck were they asking? Because it is a little vague.
Okay.
Sorry about that. I'm gonna scroll up here. Is this the one you were asking about which ones? Somebody was asking about which ones.
Yeah, number 2.
All right, let me click on this one, make it
And
bigger.
And I think what they ended up saying, like in the video, is that you go from the most curvy line to the least curvy line.
Yeah, that's one way to do it.
And that was awfully esoteric for me. It's like,
Yeah.
okay, well,
I was going to say that too, but you know what? There's better ways to do it. So I'm going to copy it, and then I'll go to my overhead. So give me a moment.
Yeah, I was able to figure out one of them, and which one, the second derivative was the only one I could figure out.
Give me a second here. I'm copying them, and then we have this line. You can barely see that. It's A is this one, B is this one. All right, so I'm gonna go to my not the best graph, but let's look at B. You will notice that B
has more
has a tangent of 0 at 0. B has a tangent of slope 0 at x equals 0. The graph A passes through 0 at x equals 0. This indicates that A is probably the derivative of B. Okay. You'll also note that B is going uphill to the right of 0, and A is positive to the right of 0. B is going downhill to the left of 0, and A is negative to the left of 0. So that's another indicator that A is probably the derivative of B. Okay, now look at A now, and you'll notice that right about here it has a slope of 0. And that corresponds to a value of 0 for the graph of C. So for the same reasoning, C is the derivative. So basically by process of elimination, C would be the derivative of A. Without numbers there, that's really all you're limited to. You're just limited to looking for where you have 0 slopes that correspond to 0 values. So the graph of the derivative would have a 0 value, where the slope of the original function would be 0. Does that make it less esoteric?
That makes it a heck of a lot more simple. Yeah.
Okay. This is true, this is true for any graph. What in the video when they say it's less curvy, that's true with polynomials. Whenever you differentiate a polynomial, you progressively get less and less. The degrees go down. So yeah, you'll eventually have a linear derivative and then eventually a constant derivative. But for other functions like exponential functions and sine and cosine, that's not necessarily true. So sorry about that. So this is a little stronger argument. This would probably hold up in the court of law.
Thank you.
Awesome. All right, let's go to the screen again. Back here to my affinity. You know what? There was a question that came up in an email, and let me find it real quick. I'm actually going to stop the share because I have to go find it. Give me a moment here. It was in the ed discussions. Yeah, it was 1.5 number 14. So let me go to that, and I'll share it here in a moment. So, okay, cool. All right, I've got it. So this is number 1.5. I'm sorry, section 1.5, number 14. I'm going to bring it up. Okay, this one came in an email. The person said she couldn't make it, but if I could ask it. So I'm going to do it right now. 1.5, number 14. Let f be a continuous function such that f of -9 is -1 and f of 9 is 1. And it asks us, is it necessarily true that f of 0 is 0? And part 2, it asks us, does there exist C such that somewhere between -9 and f of C would have to be 0. All right, so I'm going to go to my overhead. This is an example of the intermediate value theorem, the IVT. Okay, you have a continuous graph, and you know that at -9, the functional value is -1, and at +9, it's 9 and 1. So you have 2 points, and the graph is continuous. So the graph has to go from here to here. So the question is, does it have to pass through the x-axis? Is there any way to draw a continuous graph that somehow misses the x-axis? Can I hop over it? Is that allowed? Any graph that I draw, no matter what, is going to have to pass through the x-axis. So all continuous graphs pass through the x-axis. That means at some point, there is some point where it equals 0, where the functional value is 0. Okay, there's an infinity of graphs. I'm sorry, go ahead. there's an infinity of graphs, so clearly I can't draw them all, but I can infer that every continuous one is going to have to pass through the x-axis. That means it's going to have to equal 0. And so the problem is that in the first question, is it necessarily true that it equals 0 at 0? In other words, does it have to pass through the origin? No. All right, it just has to pass through the x, it has to equal 0 somewhere. Okay, so it might be over here. Maybe the graph does something like this and it shoots up to 1. Or maybe it waits and waits and waits and at the last moment goes up. Okay, the point is that somewhere in this interval, the graph has to pass through the x-axis. So in the first case, it's a little too strict. It's saying, does it have to happen at 0? No, it doesn't. However, down here, it's saying for some c, such that c is between -9 and 9, does the functional value equal 0? And the answer to that question would be yes. Okay, somewhere it passes through. And I'm going to write down here, this is called an existence theorem, or it just simply states that somewhere in there it happens. It doesn't tell us when, it doesn't tell us how to find it. It just simply states that if the two conditions are met, continuity, and then you have some information about the points, that all of the values in between have to be achieved at least once. Okay. This is a useful theorem because it's used in some of the later proofs. Now, we don't do a whole lot of proofs in this class, but it's kind of a thing that gets invoked when we have to make some adjustments. So, for example, when we get to like the mean value theorem later on, like in about 3 weeks, it's kind of like the IVT's in place again. Does this make sense?
Yeah.
Let me ask kind of a silly question here. I had this in the ed discussions. You know, it's probably safe to say that at some point in your life you stood 2 feet tall. You're probably real little, but yeah, you were 2 feet tall. And then at some point in your life you were 4 feet tall. Well, growth is continuous, so can you infer that you must have stood 3 foot tall at some point in your life? And the question would be yes. Now, do you know when that was? Probably not. But it's safe to infer that that has to be a true statement. Okay. On the other hand, if I was running a cash register and I started off with $100 and then I ended with $500, is it necessarily true that at some point I had exactly $300 in the cash register? And the answer to that would be no. It's possible I might have jumped from like 195 to 205. I'm sorry, 295 to 305. Somebody gave me a $10 bill, for example. So that's a case where growth is not continuous. So it is possible to skip over output values. That was 1.5 number 14. Got about 10 minutes. Any last questions?
Yeah, I don't know if I've reached it, but I guess I'm a little confused. Derivative versus differential, because the derivative, you're finding the slope of the tangential line at a certain point, right? So
Yes.
I guess I guess I haven't ran into differential yet, so I'm a little confused with what you're talking about earlier.
The
and
word
difference.
differentiate?
Yeah, between derivative, like
Same
the
thing,
difference.
same thing. Yeah, derivative is
Oh.
like the noun, and differentiable is, I guess, what would that be, like an adjective?
Oh, okay.
So when we say a function is differentiable, it means that we're able to find its derivative.
Okay, that clears it up. Thank you.
Sure, no problem.
Which just, I don't know if this is too far ahead, but I don't know, I think it's next section, but I haven't memorized the derivatives of the trigonometric functions. If you could do like a quick walkthrough of finding the
Yeah,
derivative.
let's go ahead and just jump through a couple of those. I'll tell you right now, I only memorized 3 of them. So if you have a sine function, its derivative is the cosine function. If you have the cosine function, its derivative is the negative sine function. You want to, sorry about that. You want to get that straight. Hold on. I need to. Can you guys see that okay? I just want to make sure.
Yeah, no, that's good.
I know it's not the best audio video, but. And then the other one that I want you to know would be the tangent. The derivative of the tan function is going to be the secant squared function. Okay. As far as the other three are concerned, what are they? You got the cotangent, secant, and the cosecant. Honestly, I never mess around with these. What I do if I have to redo, because I honestly don't remember, is I'll rewrite it as, like, for instance, the cotangent would be cosine over sine. And so I would take its derivative using the quotient property, and I should get, memory serves me, I should get negative cosecant squared. And for secant, the derivative would be secant tangent. And I would write that as 1 over cosine and then work out the quotient property. And then the last one, cosecant, and this is from memory, I hope I'm getting these right, should be negative cotangent x cosecant x. But again, these are the big three.
Okay.
And you can derive the rest using the formulas.
Okay.
Believe it or not, after all these years, I pretty much kicked those out of my brain. I just remember the first three, and then I derived the other three.
I guess could you walk me through deriving the tangent? Just because I was a little confused on
Yeah.
do it.
So the tangent is, by definition, sine x over cos x. So the derivative, if I take the derivative with respect to x, I use the quotient property. So again, we might be jumping the gun a little bit here, but this will be coming up very soon, so you all need to know this. So it's going to be the bottom cos x times derivative of top, which is cos x, minus top sine x times derivative of bottom, which is negative sine x, all over cos x quantity squared. And if you clean that up, you've got cosine squared. Here you've got plus sine squared x all over cos squared x. And the top is actually just 1 by the Pythagorean identity. So you get 1 over cos squared x. And 1 over cosine by definition is secant. So there you go.
That the one is that from the trigonometric identities?
Yes, that's the Pythagorean identity.
Yeah. Okay. Okay, that makes sense now. Gotcha. 1 over cosine is
Out of the fundamental identity that ties the two together.
okay. Gotcha. Thank you.
No problem. Any last questions?
I'm just gonna ask another one because I still confused on like d over d of x or d with respect to d of x or that.
That's just notation. That's notation for derivative.
So whenever you use d over d of x and then d over d of y, like is that just a composition of functions? I guess find the derivative of a composition of functions when you use multiple variables, or
Not in this context. In this context, I'll give you some notation here. If you have a function y equals f of x, we can write the derivative as y prime equals f prime x. That's the casual way of doing it. Or we can write it as dy dx equals f prime x. dy dx is a little more formal. Okay. The d dx notation is an operator. Okay, d over dx means take the derivative of what follows. Sometimes you get an expression that's not part of a function. And so I just need to form this derivative real fast. So like right over here, this, I hadn't yet wrote it as a function. I could have. So I just simply kind of did it by itself. So if I have d dx times, not times d dx of, let's say, x squared, then that just says give me the derivative. That's all it's doing. So that d dx notation acts as an operator. And it basically it's basically a function of a function.
Okay.
You'll get used to the notation. So this is, as you work through derivatives, not only are you getting used to the derivative forms, not only are you getting used to what they do, but you're also getting used to the wording. So like the term differentiable versus derivative, you're also getting used to the notation. So there's a lot of multiple things going on here at once. I think with practice, just by seeing a lot of these questions, you'll start to get more comfortable, like with this ddx notation.
Mhm.
Yeah, I read something that just basically said, like, when you see that, it means to split it apart. So that's what I think of.
Yeah, I'm just trying to get an explanation for everything, try to make everything make sense.
Yeah, totally.
Well, fantastic. We're almost at the end of the time period here. I want to tell you guys I appreciate we had a really good turnout. Usually I only get like 4 or 5 people, but glad we had a lot of people show up. I'm gonna put this got your message. Oh, thank you. Yeah, I appreciate the feedback. I will post this. I'll send everybody out a link. It'll probably be an hour or two. I'll send it to the whole class so you can access the video. And typically what I'll do is I'll do Zooms definitely before each test. So the next one definitely will be next Friday. My schedule is kind of funny. During the middle of the week, I'm actually not home. And so it's very difficult for me to do videos because I don't have my stuff with me. So I'm going to try to set it up so I'll probably do videos or Zooms like Fridays, maybe even Mondays, maybe Sundays or something like that. So otherwise, during the week, please rely on the ed discussions. I can check in on that pretty regularly. So again, thank you all. I'm going to go ahead and end it, and you all have a safe holiday and just plow through this material best you can. Okay.
Thank you.
Bye, everybody.